For those of you who don't know me, my name's Oliver Perks. I'm an applications engineer at Rivos. A lot of the talk that I'm going to be doing today isn't actually kind of Rivos specific. It's not about the company. It's more about the software ecosystem for RISC-V. Being pre-silicon, we aren't saying that much about what we're actually releasing, so I won't be covering any of that today. But if you do have specific questions or anything, my email address is up there, and these slides will be shared after the presentation. So, who are Rivos? Well, I mean, we're a RISC-V based silicon company, quite new, founded in 2021, and the whole idea is to have a server class RISC-V CPU and accelerator solution that can deliver efficient power and performance and deliver improved TCO for mainly the kind of AI and data analytics workloads, because that's where a lot of modern computing trends are going. And the whole idea is to be able to get people up and running as quickly as possible with existing models and frameworks. Relevant to this discussion here is something that I think often gets overlooked is the origins of the name Rivos. Rivos actually stands for RISC-V open source. So open source is in our name. It's not just part of our mandate. It's actually embedded into our name. So a lot of what we do is surrounded around bringing the whole of the ecosystem up and ready to be consumed by anyone who wants to make use of it. And we do this through upstream software contributions, working with the open source community, working with consortiums around open source projects, and really being a friendly player in the ecosystem. And that brings me on to Rise. So Rise is, I often kind of describe it as the Lenaro for RISC-V. So it's a good forum for us to operate in as a vendor neutral party. So RISC-V is, so Rise is the RISC-V software ecosystem. It's a consortium founded under the Linux Foundation, specifically for software readiness for RISC-V. And again, mandate there for open source. So this is quite different from RISC-V International, who you may already know of. Their focus is more on the hardware standards and defining what the ISA looks like. Rise is on a more practical front. How do we actually have a working software ecosystem built around those standards? I'll go in on the next slide into the members, but the whole point is that this is a cross-architecture consortium. It's not specifically targeted at any end use case or classification of computing. It's more just bringing everyone together to deduplicate effort and to address the problem as a whole, which is how to build up a software ecosystem for a new architecture. So Rise has a lot of members. These are some of the founding and general members, and you'll see a lot of familiar names on them. Many who you might not be too aware are doing many RISC-V activities, but it's a really active consortium, and it really represents a cross-industry interests for anything software ecosystem on RISC-V related. I've got a little plug on actually joining Rise, and I think one of the most important things to understand about joining Rise is that it's not just a monetary commitment. Every member commits time to this project and money. And that time is spent doing the shared development activities that are necessary to bring the ecosystem about. So this isn't just a talking shop of what should we do. This is actually assigning work to work groups, delivering on software projects, upstreaming them, open sourcing them, making them available to the whole community. And most importantly, it's doing that in a vendor neutral, implementation neutral way where everyone can contribute and have their opinions heard. And we work together to have solutions that actually benefit everyone from an architectural perspective that will really benefit everyone adopting any RISC-V hardware in the future. So I'll be talking a lot about RISE during this. There are a couple of links throughout the presentation that might be useful. And again, when you've got a copy of this, feel free to follow those links. So before I talk about software, I've kind of got to talk about the elephant in the room, which is the current state of hardware for RISC-V. And let's be honest, it's not great when we're talking about server software ecosystem. So we're pretty much only working with 2 or 3 cores that are available. And these are delivered through a couple of different single board computers. And we're starting to see a few kind of more desktop class, I guess maybe even class the Milk 5 Pioneer as kind of an early server class machine. However, there have been numerous challenges to get to where we are today. As great as the Milk 5 Pioneer is, it's based on a core that has a RISC-V Vector 7.0, so a pre-ratified specification, and that means you've got a divergent toolchain. You've got difficulties introduced through that, even though it's great to say, it's got vectorization. There are challenges there. We're starting to see a few solutions based on the Space MIT K1, which has RISC-V 1.0 implementation in there. So we're actually starting to run on some real vectorized cores, but predominantly these are still in SBCs. I think the Lychee 3As have started shipping, and they have the K1 core in as well. So they're more available, but we're still very limited. And as great as these are on a kind of enthusiast level, it's not sufficient for bringing up a robust enterprise class server software hardware ecosystem. So what do I mean when I say that it's insufficient? Well, we're going to be seeing a lot of solutions come to market in the next few years that will really reach parity with what we're seeing from x86 and what we're seeing with ARM. And a lot of the features that are required to get that parity just don't exist in a lot of these early cores and single board computers, just because they're not a focus. So we don't see much virtualization. I've already discussed the issues around vectorization, but there are extensions to all of these. So the crypto extensions, you've got the bit manipulation extensions, all things that we would expect to be seeing in server class hardware that just aren't readily available in current hardware at the moment. And then when you actually look at these solutions, they're quite weak in terms of what we need for just a software development environment. We haven't got much memory on these boards. And for anyone that's ever tried to do kind of parallel native builds of things like GCC and LLVM, you need a lot of memory to compute these things, and ideally a lot of cores. And we just don't have that available on these systems. When we're seeing 4, 8 core systems per card, it's just not good enough. And unfortunately, the reality of that is it's often faster to, well, especially cross-compile, but if you're doing anything attempting to be native, to do it in an emulation environment. And that's a really sad state of affairs, because I think we'd all like to be using RISC-V to develop for RISC-V. But kind of my favorite analogy for this is, especially as a ex-ARM employee having actually been through this, it really is like developing software for the Graviton 4 and all you've got is a Raspberry Pi. It's the same architecture if you squint, but in a realistic way, it's just not comparable. We can't do the level of development that we want on the existing hardware. So the positive sides of that is silicon is coming. There are a whole host of companies, and I include Rivos there on the list, who will be shipping server class RISC-V hardware over the next few five that I fully expect to see a bit more of a kind of Cambrian explosion going on here, where people are developing chips and silicon for their specific use cases. And the flexibility of the ICE has really allowed that to happen. And that's not just in the CPU space. We've already got a lot of RISC-V based accelerators being adopted into the market. And obviously, these are slightly easier to bring to market from a software perspective because a lot of the interface is hidden behind an SDK. When we're actually talking about server CPUs, then you have a much more mixed workload that you need to support, and the idea of software readiness is far more critical for that. So a lot of that effort is underway. It's all happening kind of behind the scenes with a hope that when hardware starts to arrive, the ecosystem is at least on its way to being ready. But you're always going to get this hardware software chicken and egg situation that a lot of software maintainers aren't going to port to hardware that doesn't exist, but people are wary about bringing hardware to market when there's not a software ecosystem to support it. So projects like Rise have been happening in the kind of back rooms to get this software ecosystem kickstarted and have something ready for when all of these companies that are involved are able to bring silicon to market. So what about the ecosystem? Well, RISC-V is a new architecture. However you look at it, we don't get a new architecture very often, and RISC-V is new, and so we've got to bring a lot of software up. And this is absolutely foundational software. This is everything that's needed for supporting general purpose CPUs, from understanding kind of boot architecture all the way up to applications and workloads that need to sit on top of that. And because this is general purpose, it's got to be able to adapt to user requirements. This isn't a case of, oh, right, we can hide everything behind a PyTorch interface and slip in some new hardware under the covers. This has actually got to be robust for everyone's use case. And unfortunately, server is actually quite a small use case for RISC-V at the moment. There's a lot of work that's gone in to get the RISC-V ecosystem ready for embedded, for single board computers, but server is a bit of a niche at the moment. Hopefully, we're going to break that very soon, but the current situation is it is a subset of the use case for RISC-V. So that begs the question, well, how do you develop an open ecosystem for server? And the simple answer is it's hard. We have a lot of the same challenges that ARM had with AArch64. You've got multiple vendors implementing the same, if not similar, cores and ISA variations based on those. And that resulted in a lot of heavy lifting for a lot of software teams. I think from what I saw with the ARM ports, it was the first time a lot of people had even considered non-x86 based code. So we'd had a kind of full decade since a lot of the power efforts, where code had just got very used to being x86. So we'd started to see intrinsics creep into code, even some cases of raw assembly creeping into foundational libraries. And it was only when we started to look to move away from x86 that we kind of realized how bad the problem was. Fortunately, I think the last few years of the rise of ARM has caused a lot of introspection from that side. People are now far more focused on portability and performance portability, and that's really helped improve the quality of cross-platform code. But when we're talking about adopting a new architecture, then we have to do a lot of work as well. We can't rest on any of our laurels thinking, oh, well, people have done it for moving to ARM. It will be easy to move to RISC-V. It won't be. There's a lot of work that needs doing, and it's more than any one company can do. The the long tail of software always means that there's going to be so much work that needs doing. But there's also a lot of dependencies on a lot of the core packages and frameworks. And what we can't afford is everyone to duplicate their effort on those fun, exciting projects. And this is what we always start to see, and it's difficult. If you're not communicating, you turn around and, oh wait, there are already 8 different implementations of OpenBLAS for RISC-V based on what people were most interested in terms of an architecture feature. So we really need to prevent those efforts, and part of that comes down to bodies like RISE that enforce that communication. But I think what really needs to be emphasized is that this isn't just an internal effort. This isn't just software vendors getting together and porting code. This is how do we reach out to the community? How do we provide the structure in place for the community efforts to adopt a new architecture? And that isn't adopting a new chip every time. So we need to find the commonality that exists within the architecture and within the ISA and exploit the tools and the interfaces that we've got so that everyone can reuse the components and all of the software that's needed to actually make it shareable. So RISC-V by its nature is built on standards, and that is the only way that it can succeed. I think everyone was very excited in the early days that it was just like, oh, it's an open ISA. I could go off and design every extension that I want, and it will be specific to every startup and every university who wanted to prove their point. And that's great, but that's not a way of operating a robust server ISA. So we really have to look through well-defined extensions. I've already mentioned some of the challenges faced by people releasing vector hardware based on pre-ratified extension versions. We really, as a community, need to make sure that what we're doing is conformant. And I'm going to talk about it a little more on the next slide, but one of the great things that we're seeing isn't just extensions, but it's actually looking towards profiles to define groups of extensions so that people can actually develop hardware and software and have a sense of conformity across those implementations. But we can't underestimate the human process here. Communication is key. RVI host a lot of different special interest groups that basically bring all of the companies together on these topics and say, well, hey, let's talk, let's share our efforts, share our activities, and make sure that we're all heading in the same direction. And what comes out at the other end in terms of silicon and in terms of software is actually fit for purpose and a good thing for the community as a whole. And they have a very strong mandate that they are friendly and open forums to discuss. So with all of that, the motivation behind all of this is, as vendors, we all need a robust ecosystem to survive. There's no way that any single vendor undercutting everyone else for their own software ecosystem is going to be a viable strategy forwards. And I always like to come back to this old adage of a rising tide lifts all boats. So by doing this work, everyone benefits from it. And that's what we want. So a bit of a mention on RVA 23 profiles, because I think this was only announced last month, off of the back of the RISC-V summit in North America last month. So this is a really important effort. So the whole point of a profile is to standardize a lot of the features that are needed for kind of, let's deem it a high performance core. So this is the extensions that are going to be used within it. And that helps everyone know, right, okay, this is a core that conforms to this profile. I can reliably tell what it implements. And this isn't about taking flexibility or choice away from vendors. There's still plenty of flexibility within the implementations. It's more about having a clear mechanism to define what is in a core. And this really helps future-proof solutions, because we can tell the similarities and the conformance between two implementations. And when it comes to software development, this means that we we know what we're coding to. This was always one of the big concerns in the early days of RISC-V, of how on earth, as a, let's say, an operating system vendor, do you produce RISC-V OS when you've got such divergence in the extensions? The only thing you can do is code to the lowest common denominator. Well, by introducing profiles like this, you kind of raise the bar on that lowest common denominator. You're able to say, oh, right, it conforms to this. I know it will have vectorization and virtualization in it. Great. That's assumed. Let's just crack on. You're not having to worry about the edge cases of systems that don't. And it does provide some sense of binary compatibility between these implementations. And that is really useful for anyone looking at ISV software or anything with binary distributions. So, with all that in mind, where do we currently sit in terms of server software readiness? Simple answer is we're doing pretty well. I think there's a general consensus that we're going broad rather than deep on some of these things, because a lot of the times we just need to get something working. The performance and the kind of deep functionality of some of these things might have to wait until there's actual hardware to work on. But for now, we've got a pretty robust set of compilers and tool chains, of developer tools for debug and profile, things like that people actually need to get running on systems. And I want to call out just a few things from here, that things like the Kubernetes work came through funding for projects like Riser. So this is everything that the whole community is doing to bring together a cohesive software ecosystem for RISC-V. And it is vendor and hardware agnostic. It's just about getting something up and running and viable, and then worrying about microarchitecture tuning at a later date. And a lot of that sits in the compilers that are seeing an awful lot of development and progress. So we're really happy with where that is. On the operating system side, I specifically wanted to call out canonical. There's a few reasons around that, but they are actually a RISE member, so they have a vested interest and commitment to developing and supporting RISC-V. They've also released a number of press releases with the likes of Ventana, stating their commitment to work together to develop a robust operating system for RISC-V with a mind of kind of Ubuntu first with a lot of these things. So that's absolutely fantastic to see. And without those level of commitment, we just wouldn't be able to deploy this at any serious level. Cool. So what does Rise actually offer? And this slide is basically just a preview to some of the other things that I'm going to be talking about in this presentation. So these are kind of my favorite hits of what has come out of it. So documentation, super boring, I know, but really important. And one of the first things that Rise did as a project was put out an optimization guide. And this just lets everyone kind of have a shared view of what it means to optimize for RISC-V. Then there's the continuous integration side of things, which is right, how once you've started building software, how do I run it? How do I make sure that all of these kernel patches that we're submitting are actually run and up to date and used rather than just bit rotting in a branch that hasn't been integrated because no one can test it. And then Python packaging. And this is a particularly important one, and I'm going to spend a bit more time talking about that. But it's, again, a really important way that Rise can have an impact on everyday development for RISC-V. So there it's kind of software outputs and infrastructure. The other side of Rise that I think is really important is at the start I mentioned that membership fees were time and money. So that money is used to fund other software development. So there are RFPs put out periodically that say, hey, like, propose work to us. What do you want to move to RISC-V? How are you going to do it? How long is it going to take? How can we help fund that work? And this is given to important cornerstones of any software ecosystem, and anything that kind of is proposed gets reviewed by a panel and then is appropriately funded. And then the other side of this is actually just developer appreciation grants that saying, hey, you know, this person possibly out on their own has gone and done this work to make their software package RISC-V ready. It maybe was quite easy for them. They just needed to add some build tests, some integration with our CI, but they're able to get this up and running and provably running on RISC-V. So let's reward them for that effort because so much open source software development feels underappreciated. So this is one of Rise's ways of giving back to the community for doing that. And don't worry, I've got links to these later. So first off, optimization guide. So again, Rise is vendor agnostic, implementation agnostic. So the whole idea of an optimization guide is how do you interpret the RISC-V specification? How do you code? And this is primarily kind of looking at the assembly level to all of these specifications. What are the best practices? What are the kind of trip hazards that we have within the architecture? How can people really make the most of it? And again, this just establishing that best practice in a vendor agnostic way really allows people to develop code that isn't, oh, well, I had access to this platform and they've got a slightly nuanced way of doing this, so I've defensively coded around that. This is about saying, well, okay, according to the spec, what's the right thing to do? And then if that doesn't work for any particular implementation and hardware, then deviate from that. But let's try and start with what is right. There are some considerations for implementation specific things because I mean the example with Elmol is yeah there are slightly different ways that you might want to do things based on your Elmol length. So it tries to be implementation agnostic, but there are a few useful tidbits in there. So I highly recommend everyone to kind of anyone interested in developing software for RISC-V, just go and have a read through this. You may already know a lot of it, but it's really useful. Cool. Porting study. So I wanted to talk about Sleef. So Sleef, for anyone who isn't familiar with it, is a fantastic library. It's read the acronym SIMD library for evaluating elemental functions. And so it's basically providing a load of vectorized maths routines. And the way it's doing it is in architecture abstraction layer. So it has vector data types that it implements that it then has specific implementations for different architectures so that you can, rather than specifically porting an application to AVX 512, you port it to Sleef. Sleef has the ability to know how to work on AVX 512, but it also has the ability to work on SVE if you move it to an ARM system, and now the ability to work on RISC-V. So this was a really important effort because this isn't just a multi-vendor implementation within RISC-V. This is how do you do it in a cross-platform implementation. So how do you make sure that nothing that we're introducing upsets the mechanisms of how it works for ARM or for x86? And there were some real challenges around that, especially when we're doing this kind of pre-silicon in a lot of cases. So there are some challenges that have already been addressed, things like the fact that RVV is vector length agnostic. Well, we've already encountered that with the SVE port, so we're able to reuse a lot of the work that went into that. But we need the extra infrastructure for cross-compiling the code and for native builds in QEMU. We need to work on build farms, but it was really the challenge of bringing everything together, both within RISC-V as a community, but actually the wider cross-architecture community. And Sleef is super important. It's one of those libraries that kind of sounds a good idea, and you think, oh, that's nice. I wonder if it works. And then you look, and actually, it's becoming really important as a foundational library for a lot of different packages, such as like PyTorch and OpenJDK. So being able to automatically improve the vectorization performance of packages like that by having the correct support in Sleef is super useful. One of my colleagues, Ludovic, gave a RISC-V Summit presentation entirely on this. So if you're interested, I highly recommend you go and check that out. But I think one of the real points that I really want to bring about with this is, again, this isn't about pushing up a branch upstream, hoping it gets merged, and rubbing your hands and calling it done. That's not sufficient. This has to be a living port. So we need maintenance and we need infrastructure. And getting that infrastructure in place was absolutely critical to the success of this additional features. So putting all of this in QEMU and running it locally, great. But this is actually about how do you integrate that with GitHub Actions? How do you get RISC-V pipelines running to actually test this on everyone's pull requests? And that means that other architectures won't inadvertently break the RISC-V support. And that's what we've seen with the adoption of a lot of kind of ARM and RISC-V now of, oh, you push it upstream. If we can't test it, we might integrate it, but no one's going to check. No one will know if it's broken because of someone else's change. This really helps keep it as a mainstream architecture, even though hardware isn't available. And then when it is, great, we could drop in a real machine and not use an emulated environment, but the infrastructure is already there, and that is the important thing. Second case study I want to talk about is around Python packaging. So this is one of those things that from an outside perspective, you wouldn't necessarily assume is a problem. Kind of Python's an interpreted language. Why would you need to worry about picking up a new architecture for that? Well, as it happens, quite a lot of Python packages aren't actually in Python. They're just API wrappers to a bunch of C++ code under the covers that, unsurprisingly, needs to be compiled if you want to use it. If it's a pure Python package, great, fine. The Python interpreters work. They'll just run everything and won't care about the architecture that you're on. But anything more complicated than that is a real challenge. And we don't want users building their own Python packages. That's not to imply people can't. It's really difficult. There are highly nuanced dependency chains that go into how you actually build and ship Python packages that come down to specific versions, specific libraries that get included, how you actually do the linking, how the R paths are set up. It really isn't something that we want users doing. And chances are, if you take something fairly complex, even on an x86 platform, and try and build it yourself, it's unlikely to work. So usually vendors build their own packages. They have well-defined build environments to do that, and they upload them to something like PyPy. And the complexity here is that you end up with a build matrix for every different architecture. You've got to consider the Python version. You've got to consider the operating system, as in Windows, Linux, Mac OS, and then the version. And so for something fairly complex like NumPy, I looked yesterday and there are 54 wheels available to download on PyPy for one specific version of NumPy. And that doesn't include RISC-V. So when we're talking about how do we actually make a software environment ready for end users, this is a big problem that we need to solve. So this is an ongoing project of work, both in terms of Rise and in terms of kind of Rivos as a whole and a lot of other RISC-V companies. So at the start of the year, we were in a pretty bleak place. RISC-V wasn't a recognized architecture. A lot of the build tools that are needed to actually build PyPy packages just didn't acknowledge RISC-V as an architecture. We had issues like, I don't know, many Linux is built on Alma Linux, which again doesn't recognize RISC-V as an architecture. So the effort to actually build packages was really challenging. And then when you actually come to do it, you've got things like you need the GitLab runners to actually go, GitHub runners to go and actually do the compilation. And because we're doing this emulated through QEMU, the build times for these are up in the tens of hours. And so most GitHub runners will just time out if you're trying to build any kind of seriously complex package. And then the infrastructure for doing self-hosted RISC-V runners also doesn't recognize RISC-V. So it was really between a rock and a hard place situation of we can't get this started. So we've just been working to break down a lot of these dependencies to understand how we can get RISC-V as uh, an accepted native platform in the Python community. So we've ported a lot of these tools. We've added support for many Linux using Ubuntu instead of Alma, and then we're able to actually port a lot of these things and get them running. So there's still a way to go, but the hope is that kind of very soon, and certainly by the time we've got hardware actually appearing, we're in a position to deploy RISC-V as a native platform on PyPy. So just to give you a kind of sense of this, because I was just messing about yesterday, if we take the dependency graph for something like TensorFlow and just graph it out, of the 38 packages that get pulled down, about 13 of them are binary distribution packages. So this is something where a wheel has been uploaded to PyPy that gets brought down as part of the install. And 25 are pure Python packages. So if you were to try and install this on RISC-V at the moment, you're going to have a really tough time because those binary packages will not play nicely, especially when you've got dependence in there for things like NumPy, which in turn will depend on things like the system OpenBLAS. And if you haven't got those versions matching, it's just not going to work. So this is really what we're trying to fix as a problem. So Rise really wanted to help address this problem. So we set about firstly setting up the infrastructure to handle this. So this is GitLab runners with dedicated resource. So we've got some beefy machines with no timeout, so we can actually do long-running build jobs that you wouldn't be able to do upstream. We've got our own version of things like CI build wheel and many Linux that have that support for RISC-V. As I mentioned, using Ubuntu as a base image for that. And from this, we're able to take a number of. We've started with the most important packages for us, but we're currently at about 25 packages. And again, for each of these packages, you are supporting multiple different Python versions, multiple package versions, all for RISC-V. And there's an active effort to expand this list. Rise is putting a lot of effort into it. We're putting a lot of effort into it from Rivos. But I think the important thing to notice is that whilst we host these all on a Git repo, the end goal isn't to own this. We want this to be mainstream. It shouldn't be a nuanced architecture that is only maintained by a special group of people who are interested in it. We want all of this to just prove that it can be done and what is required to have it done, and then it all be mainstreamed and upstreamed to PyPy and to the standard build farms. So I just want to stick a little example in here. I pulled up a RISC-V Docker image running on an x86 platform and just told it to install something simple like SciPy. And I say that because it's only got, I think, 2 dependency packages in there. So great. Fails pretty quickly because one of the dependency packages requires Ninja to build it. Great. I could look at what that is and work out how I get a version of Ninja installed on the system and then try again, and then I'll fail on the next issue around OpenBLAS. Even for someone knowing what they're doing, this is non-trivial. And that's before you've even got into worrying about version matching and everything like that. So other way of doing it is just to stick an index URL that points to the Rise GitLab instance, tells it where the packages are, and instead of bringing down the tar files and trying to build them from source, it just brings down native RISC-V wheels for these packages and is able to install it straight away. So you go from something being an absolute headache to actually that was really easy, and now I've got a working instance running on my RISC-V image. And that's the whole point of Rise, to do a lot of the heavy lifting for some of these kind of boring but necessary components in the ecosystem. So, kind of starting to wrap up with this, what are the challenges and opportunities? Well, I've already kind of outlined most of this here already. Great, we're starting to get RISC-V actual hardware. This isn't just kind of vaporware anymore. But what we have just isn't sufficient for building a software ecosystem specifically for server and cloud. Um, we've got QEMU to run things, but that doesn't give you performance. It only gives you a sense of instruction set validity. So when we're starting to look towards performance optimizations, we're really going to need something more, and preferably real hardware. Because again, expecting a user community to do that through simulators is just completely non-viable. But when we do start to do that, we're going to have to start looking at the platform specific optimization. So we're building a strong foundation for RISC-V as a whole. We've got all of these ratified standards, we've got the profiles. We need to prevent the kind of conflict between the vendors and still allow for microarchitecture tuning on these different products. And that is really where people will get to showcase the nuance of their hardware. There are architectural challenges around RISC-V. Again, this is a new architecture. People aren't used to it. We've got challenges like the fact it's vector length agnostic, the weak memory model. Again, these are problems that have been solved in the ARM community around things like SVE, but people still have to deal with them, and they do occasionally show their head. So we need to be aware of it. And again, one of the best things that Rise can help to do with that is to actually put some real money on the table to help fund people doing this. So these are the links to the RFPs and the developer appreciation grants. Again, go follow those links, look and see if anything that you're interested in doing would be relevant to that, and put your proposals in, because we really just need to bring the whole community together to improve the state of the server ecosystem for RISC-V. There are also various working groups and special interest groups within RVI. So I absolutely encourage anyone who isn't already deeply involved with all those things to get involved. They're a fantastic community. So wrapping up, bringing up a whole software ecosystem for a new architecture is hard, especially for server. I genuinely don't think I could give a presentation about software ecosystem without referencing this XKCD comic, because it's so true and we all know it's true. So we really need to just do everything we can to bring the whole community forwards and to recognize and ideally fund the effort of all of the individual players in the open source community that actually enable us to operate. Rise has been doing what it can to help kickstart these efforts, and as a cross-vendor community, it's been really successful in moving things forward and covering, as I say, a lot of the kind of boring aspects of bringing it up. And Rivos is committed to doing this. Like I said at the start, open source is in our name. We really want to be active community players within this. And this isn't altruistic. This is necessary for us. When we deliver silicon to the market, we need there to be an ecosystem that's ready to accept that silicon. And we need it tried and tested. And we don't want to be a nuanced implementation that deviates from everyone else delivering server class RISC-V hardware. So it's really important to us to act as a community and to make sure that everyone is ready to play in the RISC-V space. And with that, I'm finished. Thank you so much for listening.